In this video, we will be going over an introduction to linear systems of equations. For our first set of problems, we have been asked to solve the following linear systems or identify the infinite solution set. To begin, we will identify each of these equations as A, B, and C respectively throughout this problem. My first goal is to remove one of the variables from these equations, or two if possible, to solve for one of the variables. And so I will multiply negative 3 times equation A, and so we have x minus y minus z is equal to negative 3 times 2, and this will result in negative 3x plus 3y plus 3z is equal to negative 6. I will then add this result to equation B, which is 3x minus 3y plus 2z is equal to 16. The result is that 5z is equal to 10, and so z will be equal to 2. For our next step, we need to now cancel out a variable other than z so that we can solve for the remaining variable by plugging in z. We will start by multiplying negative 1 times equation A, which is again x minus y minus z is equal to 2, and that will also be multiplied by negative 1. This will give us negative x plus y plus z is equal to negative 2. We will then add this to equation C, which is 2x minus y plus z is equal to 9. The addition of these two equations will give us x plus 2z is equal to 7. And because z is equal to 2, we can replace this with x plus 4 equals 7, and so we will find that x is equal to 3. Solving for our last variable y, we will plug both x and z into equation A, and so we have 3 minus y minus 2 is equal to 2. Solving for y, we will find that it is equal to negative 1. And so our solution set for this system of equations is x is equal to 3, y is equal to negative 1, and z is equal to 2. In our next system of equations, we will once again label them as A, B, and C respectively. We'll begin by removing one of the variables by combining equations B and C, and so we have equation B, 2x minus 2y minus 4z is equal to negative 2, and this will be combined with equation C, which is negative 2x plus 3y plus z is equal to 7. The combination of these two equations will lead us to y minus 3z is equal to 5. We will repeat this same process and remove x by combining equations A and C. And so we will multiply equation C by 1.5. And so we have 1.5 times equation C, which is negative 2x plus 3y plus z is equal to 1.5 times 7. This will give us negative 3x plus 4.5y plus 1.5z is equal to 10.5. We will then combine this with equation A, which is 3x minus 3y minus 6z is equal to negative 3. The combination of these two equations will give us 1.5y minus 4.5z is equal to 7.5. We will then combine the two result equations that we have in order to remove another variable, and so we will multiply this equation here by negative 1.5. And so when we multiply by negative 1.5 on both sides of this equation, we will get negative 1.5y plus 4.5z is equal to negative 7.5. And we will combine that with this result equation here, 1.5y minus 4.5z is equal to 7.5. the combination of these two equations will result in 0 is equal to 0. And so we likely have an infinite set of solutions, and so we will arbitrarily select z to be equal to an arbitrary value of t. We can then use this to solve for y with respect to t by plugging it into the earlier equation that we had here, which was y minus 3 times z, which is now t, is equal to 5. Solving this equation for y, we find that it is equal to 5 plus 3t. We can now use our values of z and y in order to solve for x with respect to t. And so we will plug both of those into the equation A, which is 3x minus 3 times y, which is now 5 plus 3t, minus 6 times z, which is now t, is equal to negative 3. And so we have 3x minus 15 minus 9t minus 6t is equal to negative 3. This simplifies to 3x minus 15t is equal to 12. This simplifies to x is equal to 4 plus 5t. And so the solution set for this system of equations is x is equal to 4 plus 5t, y is equal to 5 plus 3t, and z is equal to t. For our last system, we will once again label each equation as A, B, and C respectively. We will begin by combining equations A and B. And so we have y plus z is equal to 0 for equation A, and 2x minus y minus z is equal to 4 for equation B. The combination of these two equations will leave us with 2x is equal to 4, and so we get x must be equal to 2. We will then combine equations B and C together. In order to do this, we will need to multiply equation B by 2, and so we have 2 times equation B, which is 2x minus y minus z is equal to 2 times 4. And this will give us 4x minus 2y minus 2z is equal to 8. We will then combine this with equation C, which is 2x plus 2y plus 2z is equal to 2. The addition of these two equations will give us 6x is equal to 10. And this tells us that x must be equal to 5/3. And because this x is not equal to this x, we can say that this system of equations does not have a solution. For our last problem, we are asked to determine the constants a and b to find a solution to the differential equation that satisfies the given initial conditions. We will begin by writing out our equation y of x is equal to a times e to the power of 6x plus b times e to the power of negative 6x. Taking the derivative of this equation to give us y prime of x will be equal to 6 times a times e to the power of 6x minus 6 times b times e to the power of negative 6x. Given the initial condition that y of x is equal to 0 must be equal to 12, we can apply that to our initial equation, and so we have y of 0 must be equal to 12, and that will be equal to a times e to the 6 times 0 power plus b times e to the 6 times 0 power. Simplification of this equation results in 12 must be equal to a plus b. We can then repeat the same process for the other initial condition that y prime of 0 must be equal to 24. And so we can say y prime of 0 is equal to 24. And that must be equal to 6 times a times e to the power of 6 times 0 minus 6 times b times e to the power of negative 6 times 0. Simplification of this equation will give us 24 must be equal to 6 times a minus 6 times b. And so we have a system of equations where 24 is equal to 6a minus 6b, and 12 is equal to a plus b. We can solve this system of equations by multiplying the second equation we have here, 12 is equal to a minus b, times 6, and so we will have the original equation 24 is equal to 6a minus 6b, and the multiplication of 6 times the second equation will give us 72 is equal to 6a plus 6b. The combination of these two equations will give us 96 is equal to 12a, and so a must be equal to 8. Plugging this into our equation 12 is equal to a plus b, we find that 12 is equal to 8 plus b, and so b must be equal to 4. And so the constants a and b that offer a solution to the given differential equation and satisfies the given initial conditions is where the constants a is equal to 8 and the constant b is equal to 4. That concludes this video on an introduction to linear systems of equations.